get started. So we will do some live coding later today, but this is going to be a little bit of one thing that I didn't finish up at the beginning of the week. It's not necessary, but just so that you know it exists. And then we're going to do some science and learn a little bit about machine learning, which is something that we deal with a little bit on the notebook this week, which isn't actually a notebook, but just files, and then a lot on the capstone. And one of the projects will have the option to focus on machine learning. So I'll give you an introduction without using any more math than it takes to compute the distance from one point to another on a graph. To understand the subject and the many different algorithms, you'll need a lot more math and to read a lot more, but I'll give an example of 2 algorithms, and those are the ones we're working with this week that we can understand just on the basis of that math alone. But first, let me talk to you about the pickle module. So in real life, if you want to save some cucumbers for later, you could pickle them, right? If you want to save some Python objects for later, you can also pickle them. Whoever wrote this had a sense of humor. Nico sometimes likes to ask, why did they do this? Why did they name it like this? I think the author just thought it was funny, so that's why they called it pickle.
I thought pickle was a type of vegetable.
Pickled vegetables are often things that are pickled, which is a process that you put like vinegar in a solution to preserve it.
Okay, so you can't just grow pickles.
You cannot just grow pickles. No, you put cucumbers in brine and then it becomes pickle. You can make your own. Yeah. There you go. The more you know, the more you know. So how do we, if we want to pickle, now that we've learned how to make, we've done some cooking in class too today. So basically you can you can open a file and then you can use this pickle module and go pickle.dump any Python object. And then later, days later, months later, whatever, you can load it by specifying the file, and then that'll give you your object back. So we dealt with these gravitational wave detector objects, and you had to make a bunch of code to create them. You could just save that to a file with this pickle.dump, and then later you could load it with pickle.load. You can also load or save pickle files as strings. So when I dump something to a binary file, if you look at the file, if you try to open it, it's not going to make any sense to you. Visually, you're not going to be able to tell what it is. If you open a pickle file saved as a string, you can almost read the file. It looks almost like a Python dictionary. It's a special format, but it's easier to read. However, if you have a lot of Python objects, say a big dictionary full of stuff, that's less efficient to store data that way. And we're not even dealing with this in the lab problems or the capstone problems this week, but it is useful. You might find it useful in your final project if you have to save a Python dictionary of your results to use later, and they took a long time to compute. This is an easy way to save it. So here's a little example. I'm going to import the pickle module. I'm going to make a file. Pickle.text, I'm going to open it and say it's writable, that's the W, and it's going to be a binary file, that's the B in this WB. And those are optional arguments. Then I'm making an English dictionary. We saw this dictionary before. An animal with fur that purrs is a cat, loyal animal with 4 legs is a dog, etc. And then I can save that dictionary with pickle.dump, give the Python object, and then give the name of the open Python file. And notice that this is the variable that's the open Python file. If I just put pickle.text here, it's going to crash. You have to open the file first before you give it to dump with that.
Did you just put in open pickle.text?
Pardon?
If you put open pickle.text, WB?
Yeah, you could put that whole amount instead of F, you can substitute that in here. So now if I want to use that dictionary later, say that was a big dictionary and it took me a while to make it and I want to use it later, I can again open a file. This time I want to read it instead of write to it, so that's the R. Still a binary file, that's the B. And then I just can say my dictionary is equal to pickle.load from that file. And then when I print the dictionary, it's going to be exactly that English dictionary that we saw before, or I could use it as any other Python dictionary. And you can do this with any Python object, anything. So very cool and useful. This is in the textbook too, so you can use that for reference. There's also a bunch about it online. I'm not going to say too much about it. This is just to introduce you to the concept. So far, we've met a few different ways of saving data. You can save it just to a file. You can save it to a comma-separated value file, which is basically a text file where the text is in regular columns almost, separated by a comma or a tab, a space, some sort of separator. And this is another way to save data. What's up?
So you know how the pickle saves those objects. Could you save multiple objects, like say 2 different dictionaries?
Yeah. So for example, you could, in that case, then make a list of those dictionaries. So usually I believe the pickle.save takes in one object, but you can make a new Python object that is a collection of all the objects that you want to save. So you could make, if you want to save like 5 Python objects, you can make a list of those 5 Python objects, then save that list, and then load that list again later, and then you'll have your 5 Python objects. Or you can make a dictionary of those 5 Python objects.
Can you have objects, more objects in them?
Yes, absolutely. Yeah.
So maybe you could have an object with more objects.
Yep, you can do that.
Therefore, you can pick all the things inside it by name.
That's right. So, and the best, there's actually an object in Python designed specifically for that, and that's called a dictionary. So if you wanted to do something like that, you could even make a new class that inherited from the class dictionary that had your own name, or just use a dictionary.
So don't the dictionaries require strings for identifiers?
Yes.
I think of like an arbitrary stuff.
Yeah. So you could do that as well, but your class would have a lot in common with the dictionary, so you could inherit from the class dictionary and then override its lookup method to take whatever you wanted, for example. So whenever you have something that has quite a lot in common with something that already exists in Python, it's a good idea, if you want to do something slightly different, to inherit from that so that you can use all of its benefit. So yeah, we've learned so far about saving data strings in the CSV text format. We've now learned about saving any Python object in a binary structure format with pickle. In our projects and in the capstone, for those of you who get to the capstone this week, we'll have the opportunity to learn a little bit about databases to organize our data for easy searching. One popular database choice is SQLite, and then there's a special language for accessing SQLite databases called SQL. And that SQL, it's pronounced SQL, language can also be used to access many other types of databases. There are a variety of different databases. There are a variety of different languages to access those databases. The only one we're going to work with is SQL, and I'm actually going to give you the language commands to access the database. So you don't have to learn those, but you should know that databases do exist, and they're ways of organizing information that's very efficient and searchable. So places like Google or Facebook are heavily relying upon databases so that when they have billions of users, they can find their information super, super quickly. They're not using pickle binary files. They're organizing their information in a way that they can find it very quickly. So in this class, we're not going to learn SQL. We're not going to learn too much about databases, but know that they exist. Know that if you end up working as a professional software engineer, you'll probably work with databases at some point. And this week, in the capstone, you'll have a chance. I give you a database command to go online, paste that command into the database, and then that database will give you the data back that you can then use. So you don't need to learn about the language. You can just use the command that I give you and kind of get a feel for what accessing databases are like. I already said all this. So SQL, to remember it, it's the structured query language, and SQLite is the most popular database in the world. And some of these databases are living on computers, online, but you can also make a database just on your own computer. So some programs do that. Many programs that you use might even store their data in a database that lives on just your computer. And again, you don't have to be an expert in this, but you now have heard that it exists once. And if you guys find that you need this in your projects, you're all going to have mentors for your projects. You can ask your mentor to work with you to help you save your data in Pickle or to help you save your data in a database if you decide that's a good idea. I'll just finally, the last part about Python is give you an overview of Python's many built-in modules. RE is a module that helps with pattern matching. We learned about regular expressions in the bash console when we were using star to kind of access any types of files. RE is the module built into Python that allows using regular expressions to match patterns. So it is a typo. Yeah. So I am allowed to say different things than on this slide. So, but yeah, I will correct that. So OS is a variety of operating system-specific tasks. This allows you to do anything you might do from within the bash console easily from within Python itself. Make dir, change dir, ls, all that sort of stuff. Sys is a variety of interpreter-specific tasks. This is what we use to access the arguments of a Python program when it is running from the command line. Datetime is a module that will let you access the date and time. Timeit will let you time certain functions. So eventually you might want to improve the performance of an algorithm or of something that you're doing. So you can measure its initial time and then try to do an improvement and see how long it takes to run the second time. URLlib2 helps you access content from the internet via URLs. And there's many examples when you look at AstroML or any of these modules that we're using who are accessing the internet. Often, if you look at their source code, you can see they're using URLlib2 in there. We've already seen random in math. Random helps us create random numbers and random selections. And math is a variety of simple mathematical functions. NumPy contains many more with the added advantage of the features of operating on NumPy arrays. But math has cosine and sine and pi and some basic stuff, square roots, etc. there. And again, this is more to teach about each of these modules. It would take a while. And I don't want to bore you with all that. The best way is just to learn them. But to learn them, you need to know that they exist. So if you need to match a pattern, you need to do something on the bash console, if you need to time something, if you need to access the internet, know that there are standard modules in Python. These are the most popular ones. And see if any of them work before trying to write something on your own. OK, so time to get to some science. I won't get too much into the different type of data that we're dealing with here. One of the projects we'll get to do a lot of investigation into this. But broadly, there are two different types of astronomical data. Photometric data measures flux or intensity of astronomical objects, of their electromagnetic radiation. And spectroscopic data measures that electromagnetic radiation as a function of its frequency. And we saw one of our speakers, Dr. Ramirez, gave us a little plot yesterday where we saw some lines and some dips, etc. And that was basically spectroscopic data. And that data can give us information about how the radiation interacted with matter, and clues as to age, speed, and composition of astronomical objects. Doing spectroscopic data, because you have to have it as a function of frequency, is a little bit more difficult than taking photometric data, which basically just says, like, what's the flux of the light? That's all I need to know. So many more objects that humans have observed, there's photometric data than spectroscopic data. Or if there is spectroscopic data, sometimes the data is maybe not, there isn't as much of it. Maybe it's not as high resolution in terms of the number of objects, etc. But that's sort of the basics. You'll hear photometric, spectroscopic data in terms of astronomical observations. We also got to meet in one of the homework problems this concept of projections. So this is just to emphasize, here we have the Earth, and the Earth is a sphere, kind of an oblate sphere. It's not exactly a perfect sphere, but roughly it's a sphere. And if we wanted to represented in 2 dimensions, we have to somehow change the sphere to splat it onto a page. And there are a variety of different ways of doing that. And we played with some different projections in our problems this week. And here you can see a visualization of different ways of kind of splatting a sphere onto the page. And that's important not just for the Earth, but if we look at the sky is basically forming a sphere around us. You look up, there's a sphere wrapping the Earth that's basically the sky. And so if we want to take our observation of the sky on the north of the Earth and of the south of the Earth and everywhere and put it on 2 dimensions, we have to do the same splatting from the sphere to the 2 dimensions. So that's what you're seeing when you see several of these problems. So for example, here's a galaxy survey, and we see that we don't have data for all of the sky. There's just a little portion of the sky that we have data for. And to represent that data in 2 dimensions versus 3 dimensions, we had to do that same splatting, project it. And so that's why you see these projections. So I'll give a couple overviews of the data that we have access to in AstroML. One is the Sloan Digital Sky Survey. This is data taken at the Apache Point Observatory in New Mexico. It has photometry, so that's flux or intensity, for hundreds of millions of stars, quasars, and galaxies. It has spectra for several million. Again, I mentioned spectroscopy is a little harder to get than photometry, so only several million of those have spectroscopy. And there was a second phase of the same survey that repeated the observations for a smaller portion of the sky so that scientists could study those objects over time. And this is what we'll practice in the capstone using a database query to query this database. So this data is accessible to the public, to any of you. And you can access it in the same way that professional scientists do and use it. It's not secret. And in principle, if you had the same training as those scientists, you could make discoveries. And you may even do so in your projects. Who knows? So here we basically have plotted the age of the various galaxies, where dark is closer to the present and light is closer to the past. So a bunch of galaxies on the sky. There's also the NASA Sloan Atlas, which has images and parameters of local galaxies derived or computed from the Sloan Digital Sky Survey imagery. It also includes Galaxy Evolution Explorer data for the ultraviolet part of the spectrum. So here we have the locations of the galaxies in that atlas, which have a little bit more information about them because scientists went and derived a lot of parameters from the original data about these galaxies. There's 2 more data sets I'll go over, and then we'll get into some machine learning. So the Lincoln Near-Earth Asteroid Research Project is an MIT Lincoln Laboratory program. It's a project to catalog near-Earth asteroids, also referred to as near-Earth objects. These objects potentially threaten Earth, so it's a good thing that they're looking at them. This data set, just on accident while they're looking at these objects, also includes a lot of images of the sky that can be used to detect stars and their variation. So this data set, how AstroML is using it in the plots, is actually not for the asteroids, but to just look at, while you were looking at the asteroid, you captured some stars too. Let's look at what the stars were doing over time. So we're able to make plots of various things having to do with those stars. The last data set I'll go over, and this is actually the data that I was collecting when I was serving running the South Pole Telescope, is data about the cosmic microwave background radiation, which is electromagnetic radiation from shortly after the Big Bang. It is best detected far away from the atmosphere and space. The WMAP satellite is one such satellite that was put up there to detect this. It can also be detected from remote, high, and dry, temperature-stable places such as the South Pole, which is where I was. And this... Pardon?
Is that temperature very quite a bit in the South Pole?
So it's cold all the time. And because there's no what's called a diurnal cycle, which is a day-night cycle, it's either all day or all night, it's basically the atmosphere is very stable. So a place like the desert, so you need something high and dry. The South Pole is a desert, but usually deserts, I don't know if you've ever been camping in the desert, but it's really super hot during the day, and then it gets super cold at night. You have to like bundle up. So at the South Pole, it's just cold. Cold, 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 cold. There's no like day and then at night you have to bundle up. You just always have to bundle up.
The reason I said that is because the temperature varies between like 20 degrees Celsius at really high, maybe 0 degrees Celsius at normal high, to the negative like 100 Celsius.
So, but that's not within a single day. So usually.
So I guess it's because the temperature changes over a much longer time.
Yeah, so it is the case that during the summer, the average temperature at the South Pole is something like -20, and during the winter, it's closer to -70. Over the year, it's -50, so there is some change over time, but you can more statistically model that. If the temperature is changing really quickly, we do long observing cycles, so you basically have to throw away some of the data. In addition, the mirror actually changes when the temperature changes. So if we had this hot and cold sort of thing going on, the actual physical mirror would warp and change, which would be very annoying. So this is just, again, we see this here. It's actually a sphere around the sky of the WMAP data from the Big Bang and from elsewhere. What do you think this band in the middle is that's all red? That's hot. That's the Milky Way. So that's something that.
Oh, that's what these things.
Yeah. So that's something that scientists are actually, with this data, interested in trying to look back to the Big Bang. But there is also some things in the same kind of temperature window from the Milky Way itself, and we have to filter those out and ignore those. So that's all the red there. So there are many models for how to ignore the data from the Milky Way. And these models can get so complicated that one of the other telescopes at the South Pole reported a detection of a particular feature from the Big Bang having to do with gravitational waves. And it turns out they just hadn't modeled the Milky Way correctly, and they were seeing something from the Milky Way. So scientists make mistakes too, and you can see a lot of the Milky Way stuff by eye, but you can't see all of it by eye, and it's very important if you're going to make predictions to remove the stuff from the Milky Way. AstroML that we're working with here is a Python module for machine learning and data mining built on NumPy, SciPy, scikit-learn, matplotlib, and AstroPy. So the reason why I mentioned that is AstroML gives us tools for downloading these data sets, which is super nice. That said, if you do your own machine learning for any other problem, say you want to predict what movies your classmates like, say you want to enter an online contest to do predictions, Netflix has had prizes of up to $1 million for these contests. There are prizes. I'm linking you to a website, one of the capstones we're doing was originally a contest, and the winners got $60,000 for predicting these things very well. You do predictions, and it's not with AstroML. You use scikit-learn, and that has all the machine learning algorithms that are many of the machine learning algorithms that are easily accessible from Python. There's also a variety of other modules, but in general, the first place to start out is try existing machine learning techniques and then see if anything works well. Once you get that set up, then you can try to make improvements. So AstroML contains a library of statistical and machine learning routines for analyzing astronomical data in Python. It also contains loaders for several open, that means open to the public, astronomical data sets, and it contains examples of analyzing and visualizing these. So we're using that this week. So now we get to learn. Yeah.
AstroML have anything to do with astronomy? Why is it named Astro?
So it is a library of statistical and machine learning routines for analyzing astronomical data in Python. So it gives us access to all the data sets that I just showed you, easy access to loading and working with those. So all the problems you're doing this week and the capstone are using AstroML to do these analyses of astronomical data in Python. Scikit-learn, which it's built upon, is a little more general. It's kind of for anything, any sort of data set, but AstroML focuses on helping you do machine learning on astronomical data. Okay, so let's learn just a little bit about the algorithms. And I'm just going to teach you what you need to know to use them. I'm not going to teach you what you need to know to implement them. I'm not going to teach you about every algorithm out there. I'm going to teach you what you need to know to use a machine learning algorithm. So what is an algorithm at all? An algorithm, I looked this up in a dictionary, is a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. So things you might need an algorithm for would be for sorting a list, for finding a route. Google is using algorithms when it tells you which directions you should go. One of the final projects in my computer science class, this wasn't even a final project. This was just a homework assignment. We had 1 week to do it. They gave us a database of streets, and we had to implement Google Maps. So we will have more time to do our projects. But one of the things that we had to do was basically come up with an algorithm to compute the best route from A to B. And luckily, there's examples out there of good ways to do that. So didn't have to invent things from scratch, but had to implement it so that it worked with our data. Algorithms are also used for searching for data efficiently and a huge number of other tasks. I'll just use the word algorithm so that you know that's what I mean. It's basically the set of rules to be followed in calculation. And those can also be statistical. So it's not that these rules can be determinate or have to be determinate. You could say half the time do this and the other half of the time do this. Randomly flip a coin, and if it's heads, do this. That's also an algorithm. What is machine learning? Machine learning, you might also hear artificial intelligence. You might hear deep learning. You might hear let's see, a variety of other terms for it. And when I'm using it in this class, I mean it's a collection of algorithms to help machines learn from data. There are two types of machine learning in general. One is unsupervised learning, and that's when you don't have any information about the things you're trying to learn about. You learn by putting them in clusters. It's descriptive, it's not predictive. That means you can describe things that exist, but if you give me a new thing, I can't necessarily tell you much about that thing. Supervised learning, we have an answer key, a cheat sheet for some of the data giving the answers that the algorithm would have if it worked well. This is called training data. And that means that you could predict something. If you give me a new piece of data, I could say, based on what I've seen so far, this is what I think that data is. Then there's two types of things that you can predict or learn. You could predict something that can have a continuous value, like the speed of a car, whether it's 65, 64, 63.2, 63.2729. Classification is something where we want to predict something that can have a few discrete values. Say we want to predict what kind of fruit this is, and we know there are only 20 types of fruit in the world. There might be more than that, but someone gives me a new fruit, and I'm a machine, and I want to predict what type of fruit this is. It can only have 20 values in this example. There are a huge number of algorithms out there to help you do this. These are just the ones available in scikit-learn, which AstroML is built on and which you can use for other uses. There are many more out there, and we're only going to learn 2 of these. So the 2 that we're going to learn today about are k-means, right here, and we're going to learn about k-neighbors. So you see there's a huge amount that I'm not teaching you that you can also check out online, and this isn't even what Google or other places are doing. There are many, many more algorithms out there. So we'll use k-means in a case where we have enough data, more than 50 samples, where we want to predict a category, where we do not have labeled data, where we have a good guess as to the number of categories, where we don't have too much data. then we'll use k-means. And we'll use k-neighbors. We have enough data. If we want to predict a category, we do have labeled data. We don't have too much data. And I'm not teaching you about this algorithm yet, but it's a little bit, it involves more math, but it's a little more efficient than k-neighbors, which we're going to learn about. So I'm teaching you about k-neighbors just because it's easier to show you about. But you can also use this linear support vector classifier instead. So I'm not going to teach you about this, but this is usually what, if you want to be very efficient, you would try first. And we don't have text data. So just teaching you about these two things, and you can see that they're not always applicable. For example, if you want to predict a quantity instead of classifying something or clustering it, we wouldn't use either of these algorithms. If we wanted to predict the speed a car is going based on its color or something like that, that would be predicting a quantity. And so we're also not learning about any algorithms to do this. There are a ton of tutorials online. So if you're curious, there's a Stanford professor who has machine learning introduction for beginners that you guys all have the ability to approach now. And it has short exercises that are even easier than the ones that I give in this class. Okay, so let's see when we might use machine learning, one of these two algorithms I'm going to teach you about today, and how we might use it. What do we need to know to actually use it? So these are a couple exercises from an introduction to machine learning for students in secondary education. And secondary education is high school. So if we wanted to sort United States coins, just a few of them, we would need to know something about the United States coins, probably. If we didn't know anything about them, we might try to sort them on a pile and see if we could group them together. Might help if we knew the number of different types of coins. And there are machines that actually go ahead and sort coins. You can take it to Coinstar or whatever, and the machine will sort it for you. If we just had a few coins to sort, it's not a big deal. It's just by hand, kind of pick things out by eye. If you had thousands of coins, you'd want to use a machine, a physical machine to sort the coins. And if you had digital coins, you'd want to use a digital machine. So if we're sorting foreign coins where we didn't know anything about them, beyond that there are 20 types, many are worn down, and we have millions of coins, how would we design an algorithm to sort those coins if I didn't tell you anything beyond that there are 20 types of coins? You can see a bunch of different Indian coins here. So if we wanted to sort these coins, what are some things that we might use to sort them by without knowing anything else? Nayeli? Size. So we could first sort them by size. And we'd have some big coins, and then we'd have some small coins, and we maybe assume that that would be a good thing, that probably this coin isn't the same as this coin. Sounds like a good idea. Other good ideas of things to sort them by?
Color or what their marker is?
Color and what their marker is. Sounds good. Yeah, so we could sort them by like gold versus silver. It would get a little ambiguous because sometimes maybe this coin is the same as this one, and it's just dark because it's worn. So it's good that we have many different features to sort by. So we could also make a guess as to what it says on here. And for the non-worn coins, it might be easy. Like I can kind of see that this is a person here. For the very worn coins, it might be a little hard. But we can make our best guess. And the good thing is, because we're sorting them also by size, that this isn't exactly the same size as this. So that also helps. So it's good, especially in these cases where the data, the thing that we're trying to learn about, it's not always clear and some of it's messy, to have more than one feature, more than one thing to sort by. Any other ideas of what to sort by? So far we have marker, we have color, and we have size. Any other ideas? Crystal?
Shape.
Shape. Yeah, great idea. So we have some square coins here, and we have some round coins. So that's a great feature. And maybe one more idea what we could sort by. We have marker, color, size, shape. I think weight could be a good one too.
Oh.
Yeah. Which is helpful if we have the whole coin, but again, some of these are worn, so it's not always going to be perfect. Like maybe some of these are broken too. But often, especially in ancient times, if we're dealing with ancient coins, like the weight was actually what made its value rather than just the symbol. So again, you can see here that we have to have a number of different features. You have to select what we're going to sort by when we decide we're going to sort these coins. And then we, without knowing much about the coins, it helps us if someone says there's 20 types of coins. So that after we do the sorting of these million coins, if we come up with only 5 types, maybe we're doing something wrong. If we come up with 45 types, we're definitely doing something wrong. And it helps that we have these redundancies because some of the coins are damaged and stuff like that. So maybe we can't tell by the marker what it is, but we can tell by the weight, that sort of stuff. So very good job in coming up with all these features to sort coins by. And this is exactly what we have to do when we do a machine learning exercise. There are ways to automatically select these features. There are algorithms to do that try to do that. But the algorithms we're going to learn, we as humans have to select the features to say, dear computer, I have some coins. I have some data about the coins in a giant NumPy array that has their weights and their colors and all these different features. And I think there are 20 coins. Could you give me a grouping of the coins? And the algorithms that we're learning today will give you a grouping of the coins, which is pretty cool. So what would be a bad feature to sort these on? If I sorted something incorrectly, like what would be, we picked a lot of good ideas for features. What would be a bad idea for a feature?
How worn it is, maybe?
How worn it is, yeah. Maybe that is, maybe the type of coin is independent of how worn it is. You can have a coin, like you could have a nickel that's really worn and a nickel that's not really worn, and they're both nickels. It doesn't matter if they're really worn or not. And so there are a variety of, when you're thinking about the best features to sort your data on or to learn from, picking bad features is also something that you might be prone to. You might think it's a good thing to sort on, and then you'll see it's not good. If you decide to sort on a bad feature, it'll slow the algorithm down, it'll confuse the algorithm, it'll maybe cause additional problems. So it's up to you to select features. Conversely, the fewer features you select, if you can tell all the coins apart just based on color, then giving it all this other information, the weight, etc., is just going to slow it down. So if there's a feature where you can tell it apart just based on that, then it's best to just give the algorithm that. So these are all things that are the art of machine learning. So it's up to you as the person using it to select what the features are, to play around with it, maybe remove a feature and see if you get the information out. Imagine we want to teach an algorithm to distinguish between a banana and an apple, just those two fruits. And I have a basket that has bananas and apples only in it. We can select the features that the machine should use to do so. And here I've given you, say this is all the data that I have about the apples up here. I have the weight, the color, and the price. This is of the apples and bananas. So which of these features do you think would be good to use and which would be bad to use? Color would be good, yeah. Is there anyone that would be a bad one? Price, yeah. Because, I mean, maybe you go to Trader Joe's and it's one price. Maybe you go to Whole Foods and it's twice the price,
It's the same store. Price divided by weight might work.
Yeah, if it was the same store. But I think
some machine learning algorithms use that, by the way? Do they, divide the
yes,
weights?
absolutely. That's a great question. So sometimes a technique can be called feature reduction. So the algorithms perform better the fewer features you have. So sometimes you can combine features by taking one and dividing it by the other, for example. Or you can even do something like normalize the features, where instead of, we assume that there's a maximum weight, and we normalize everything so that the weight's between 0 and 1, and the price is between 0 and 1. So there are a variety of different things. So let's decide here that price is not very useful in this case. Color is useful. What about weight? Do you think that'll be useful? You think it's useful?
So when you said it about having it arranged, because if you notice that the red, which is the apples, are higher in the weight than the bananas.
Yeah, and that's
Hey,
great.
why is it useful at all? Why is the one that weighs less, apple that weighs less, cost so much more?
I don't know. I think I bought it from Whole Foods. But that's great, Nayeli. So that also shows that all you guys are great machine learners. You know, the fact you are all better than the computer at this. And you've learned an amazing amount. So these machines are much dumber than you are, and remember that when you're programming Python, that you are smarter than the machine. And we saw this. You spotted it right away, but to teach a machine that, we're going to have to do some math, whereas you just saw it in your head, because we're brilliant. Humans are brilliant. So you can, in principle, use as many features as you want. I could have hundreds of features. Features which don't help will be pointless to use. Too many features will cause the algorithm to be slow, among other problems. Choosing which features to ignore is equally as important as which features to pay attention to. And you guys already did this, and we already did this as well. For the US, for the foreign coin starting example, what would the features be? You don't even need to be a machine learning expert to try to do this once you realize that the feature selection is important. So that's basically all you have to do to use a machine learning algorithm. Choose the features. And the last thing you have to do is, the computer doesn't know what yellow, red, etc. is. We're going to have to represent these as numbers so that the computer knows what it is. So we have to choose some representation for the features. The only bit of math that we're going to need to understand a little bit about how the computer actually does this is what's called the Euclidean distance. But you've already probably done this in all your math classes. So if we have 2 points, one is at 0, 0 on a plot, and one is at 1, 1, how do we compute the distance between those 2 points?
If there was a C squared equals C squared, right?
Yeah, so, but what's A, B, and C? So A would be like here, and B would be here, and we want C, which is the distance between these 2 points. So how do I compute that, given their coordinates? Yep? Okay, so let's say this is x2, and this is x1. So what's x2 minus x1? What's 1 squared? 1, okay. Now what's y2 minus y1? 1. 1 squared? Okay, so what's 1 plus 1? 2. And then we're going to take the square root of 2. Right? That's the distance between A and B. So that's great. I used, because I think so 1 minus 0 plus 1 minus 0, square root of 2. That's in 2 dimensions. We can also do that in 3 dimensions, 4 dimensions, arbitrary dimensions. We're not going to visualize it all. But instead of x2 and x1, I use x1 and x0, just because I think starting from 0, because I like Python. So this is a general formula. If we have, in 2 dimensions, coordinates for points x, y, we can compute their distance. In 3 dimensions, if we have 3 coordinates, it's the same formula as above, except we have also the z. z1 minus z0 squared. Still the square root. And we can visualize.
X is 0.
Pardon?
X0.
X0 is the coordinate of the first point. And x1 is the x coordinate of the second point. Y0 is the y coordinate of the first point. Y1 is the y coordinate of the second point. And here's z0, the z coordinate of the first point. Z1 is the z coordinate of the second point. So their distance, we just add in. We have the same thing as up here, but we add in the z1 minus z0. And this is also easy to visualize. What's the distance between this point in 3 dimensions and this point in 3 dimensions? The stick, the length of the stick. Now, if this was in 4 dimensions, I'd be in trouble. I can't visualize it, but I can still compute it. Because we have the same thing as in 3 dimensions. This, only I've added a 4th dimension, the W. So there's the 4th dimension coordinate minus the fourth dimension coordinate of the first point. Second point minus first point squared. And you can do that for as many dimensions as you want. And for every dimension, you just add them. It's easy. And the computer will actually do this for you. The only reason why, in terms of the algorithms that we're using, you don't have to input this. But I'm telling you about it because what we're doing here when we represent the features by numbers is each of these things is a feature. X is one feature, so that here in our banana-apple example, we have two features. We have color and we have weight. So the x coordinates could be the color, and the y coordinates could be the weight, for example. And we could also have a bunch more features. Like our coin example, we had a ton of features. The x coordinates would have been like the color, the y coordinates would have been the size, the z coordinates would have been the weight, the w coordinates would have been the shape. We had many more coordinates out there. And for each one, you're going to need to have numbers, and the computer will compute the distance between one point and another point in that feature space. So this is internally what's going on. And this is why we select those features, why we select them as numbers, because the computer needs to be able to compute the distance between one thing and another thing. And we'll see that in a chart here. So to use the algorithms I will outline today, we need a concept of distance between features. We will represent all our features as numbers, so we can use the Euclidean distance for this. And the apple-banana example, we will choose two features to use and represent them as numbers. Two features is easy to visualize in a 2D graph, but we could have as many features as we wanted. So here I've chosen to represent the color in a 3-bit RGB. So 6 is actually going to be yellow here, and 4 is red. And now if I plot this, Nayeli did this in her head, but the machine can do it too. So where do you think, so 6 again is yellow and 4 is red. So where do you think the bananas are on this plot?
Which one's yellow?
6 is yellow and 4 is red.
Oh, I'm guessing it's 6.
Yeah, so the bananas are over here. And then 4 is yellow, so or 4 is red, so where are the apples? Yeah. And you can imagine actually having gradations of red. So maybe you could have, this point could be a little bit here, this point, maybe the apple's a little brown, it's here, this point's a little here, this point's a little here. They can kind of move around here, but the computer is going to be able to, when you represent the color as numbers, the weight as numbers, to learn that these things go together and these things go together. Even if you don't tell it that there are apples and bananas, you say there are two types of things, here are the numbers of the two types of things, learn it. How it does that is something called k-means clustering. And this is machine learning. It's unsupervised, meaning we haven't labeled any of the data that's apples or bananas. We choose the number of clusters. We're going to say there's two types of things. Then we're going to choose k centers randomly. So here k is 2. So basically that would mean in this previous plot that we choose 2 centers randomly. So we could choose this point and this point. We could choose this point and this point. We can choose this point and this point, this point and this point, whatever it is. 2 things randomly. Then the algorithm is going to calculate the distance from every point to every center. So say we chose these 2 points. The algorithm is going to be like, what's the distance of this point to this point? What's the distance of this point to this point? What's the distance of that point to this point? What's the distance of, every single thing that's not a center to the center? And we know how to compute the distance. Then the algorithm is going to pick the closest center for every point and assign it to that point. Then it's going to take each group and compute a new center based on the average x and the average y here in 2 dimensions. And then it's going to do it again, and again, and again, and again, until the center that you calculated, the group, doesn't move anymore. And what that will do is it will find, let's see, we'll go in a second with the apple and banana examples. So we use this algorithm when we have enough data and we want to predict a category. You don't have any labels, apples, bananas, etc. You know you can guess the number of categories too. You have less than 10,000 items of data to work with. If you have more than that, your algorithm might be too slow, so you'll have to choose a different one. So here with the fruit, we had already this example, and k-means will come up when you feed it the information with this cluster and this cluster here. And there's an example in the capstone of actually using k-means on astronomical data to classify different types of stars, for example. There's another type of classifier that I'll teach you. So there was k-means. Now there's k-nearest neighbors. And k-means is used when you don't have any labels on things. K-nearest neighbor is used if you want to classify things if you have some labels. Not on everything, maybe on a couple fruits. I've told you this is a banana and this is an apple. Not for all the fruits, just for a couple. To classify an object, you find its k-nearest neighbors in the labeled training data. So say 2 nearest neighbors, then you take the majority vote of the neighbors. So in our example here, say I tell you this is an apple and this is a banana. And say I've set k equal to 1 in this case. What's the nearest point to this one? Right here, right? And I've told you that this one's a banana. And so we're going to take we've set k to 1, just your one nearest neighbor. So the algorithm will be like, okay, that's a banana too. Sounds good to me. Then what's the closest point to this point? Up here. And I told you this is an apple, so we'll just make this an apple, the one nearest neighbor. And what's the closest point to the top point? Again, an apple. So it's like this is an apple. So you use k-nearest neighbors when you have a few of your points, you have some information about them. You wouldn't use it if you didn't know that any of these things were bananas. What would k-nearest neighbors tell you everything was?
The same thing.
It would tell you it was an apple, right?
Wait, what?
Yeah, because k-nearest neighbor only has, if I removed the information that this one's an apple and this one's a banana, if I say, I don't know that this one's a banana, I don't know what this is, it's going to find...
But it still knows the other one's an apple?
It still knows the other one's an apple. Yeah, yeah. So it'd be like, what's the nearest thing that I know what it is? The nearest thing it knows what it is an apple, so it's going to be like, this is an apple.
So first you need to know what you're looking for?
Yeah, with k-nearest neighbors, you have to have some information about your data, the labels of stuff, and the more things that you have labeled, the better the algorithm is going to do. Because otherwise, say in our coin example, if we didn't have any labels for one type of coin, it would never discover that. Or say that one type of coin that we have labeled is actually a really bad example. It's like broken, it's the wrong weight, everything like that. The thing that'll be closest to it might be something that's square, even if it was originally circle, because it's broken. So your training data, your labeled data, the better that is, the more likely your algorithm is going to give the correct answer.
Do you have an algorithm that, say, if it was far enough from all the other ones, like far enough from the average distance between the ones of the same type, it would just make it a different type?
Yeah, so there are a variety of improvements on all these things. In existing algorithms, or for your particular problem, if you find that for some reason it's not classifying something, you could even artificially go into the data and look with your eye and say, here's an example, I know that this is this type of galaxy, I'm going to label it even though it didn't exist. You can add things in like that. There are a lot of improvements. The thing in the end is that you can have a good idea for an improvement, you want to test it for your particular problem and make sure that it works well. So that's machine learning. You guys know how to do it. You select the features.
Can you have like algorithms in algorithms?
Yeah, absolutely. Just like an algorithm is just a procedure for doing something.
So like if you have
So,
another one, it'll cut it off.
yeah.
Like this part of it, something else.
Yeah, so an algorithm isn't a Python concept, it's a head concept. Usually algorithms are put inside a function, And you can have functions inside functions. But an algorithm is just a concept, a procedure for doing something. So how to add two numbers when you learned in elementary school, how to carry the ones and to like add two-digit numbers, that's an algorithm that you learned as a human. And maybe now you can do it in your head without thinking too much, but if you have like, if you're adding 57 to 63, that's a little easier than if you're adding 1,579 to 2,672. You might have to think a little more, maybe even write something down, who knows. We learned about k-nearest neighbors. So the important thing here, we want to predict a category, in this case apple or banana. You have some labeled data. You haven't learned about this other algorithm where it isn't working. I'm not teaching you about this other algorithm because it requires a little bit more math. All the math that you need to understand what's going on here is just that concept of distance, and you don't even need to implement that. Python, scikit-learn is doing that for you, but this will give you an overview when you're selecting your features for machine learning, what type of features might be good. Again, here I give an example where I had two labeled points. I have two things that I've told you what they are. We had a human identify it, and I have hundreds of other fruits in this giant basket, which I want the machine to figure out what it is. So we can see what k-nearest neighbors would do with that here. So I've bolded the ones that I labeled, and then the machine comes up with the other ones, bananas and apples. Okay. That is actually it, and we'll do some live coding this afternoon, but you should feel very proud of yourself that you guys get more about machine learning than most scientists. Cool.
The axis, how does it deal with the axis? Because, say, one axis is a lot larger than the other, couldn't it mean that it would show it as much larger and different?
That's right. So I did mention something about sometimes it's good, it depends on your problem, you can try different things. This is, again, in art. You can do something called normalization, where you could try to set everything between 0 and 1, for example, or 0 and 10, so that they're similar sizes. And you might find that that makes your problem work better. You might find that it makes it work worse. Probably will make it work better, but that's a good idea, and that's called normalization or regularization. But you can still, without doing that, try, and if it gives you apples and bananas and everything's correct, then you don't need to do any more work. If it's then giving you the incorrect things, that's when you have to say, I have to be a little more clever about this. Okay, we'll take a 5-minute break and then go over to East Bridge.